Why do quantum terms sound so scary? Tonight, we're going to discover why quantum physics has the most intimidating vocabulary in all of science. You've probably heard words like superposition, quantum entanglement, and wave-particle duality, and immediately felt your brain shut down. But here's what most people don't realize. These terrifying terms are just fancy names for surprisingly simple ideas. Scientists love making things sound more complicated than they actually are. By the end of this journey, you're going to understand that quantum physics isn't some mystical realm of impossible weirdness. It's actually more straightforward than you think. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Settle in. This is going to be beautiful. You need to understand something fundamental about how we got here. For millions of years, human brains evolved to detect predators, find food, and recognize faces of social group members. Think about this for a moment. Our ancestors who survived were those who could spot a lion approaching across the African savanna, identify ripe fruit in trees, or recognize whether that figure moving in the distance was friend or foe. Every instinct you possess, every gut feeling about how the world should work, was shaped by these ancient survival pressures. None of these evolutionary pressures selected human ancestors for their ability to understand the behavior of electrons or photons in motion. Your intuition works perfectly for objects the size of rocks, the speeds of running animals, and distances of a few hundred yards. When you throw a baseball, your brain automatically calculates trajectory, accounting for gravity and air resistance without conscious thought. When you walk across a room, you navigate three-dimensional space effortlessly, predicting where furniture will be and how much force you need to open a door. But the subatomic world operates on scales billions of times smaller than anything human senses can detect directly. A hydrogen atom measures approximately 4/billionths of an inch in diameter. Let me put this in perspective. If you could enlarge a single atom to the size of a football, that same football would be the size of planet Earth. The atomic nucleus is even more absurdly small, like a solitary marble sitting in the center of a completely empty football stadium. At this extremely reduced scale, the rules that govern footballs, cars, and planets simply stop working in predictable ways. Imagine trying to play billiards where the balls don't follow straight lines, where they can be in multiple places simultaneously, and where the very act of looking at them changes their behavior. This isn't science fiction or philosophical speculation. This is the verified reality of how matter behaves when you zoom in far enough. The fundamental problem isn't with the universe, but with the fact that classical physics is merely a useful approximation for large scales. Isaac Newton published his Principia in 1687, establishing laws of motion that work perfectly for macroscopic everyday objects. For more than 2 centuries, physicists assumed Newton's laws applied universally, from grains of sand to distant galaxies. And why wouldn't they? Every experiment confirmed it. Every prediction worked. Newtonian mechanics predicts precise trajectories. Knowing initial position and velocity allows you to calculate where any object will be at any future moment. Drop a ball from a 10-story building, and Newton's equations tell you exactly when it will hit the ground and at what speed. Fire a cannonball at a specific angle, and you can predict its landing spot to within inches. This total predictability created an illusion of absolute determinism, as if the universe were a giant clockwork mechanism, perfectly predictable and mechanical. The philosopher Pierre-Simon Laplace proposed that an intelligence knowing all positions and velocities could predict absolutely the entire future of the cosmos. Picture this cosmic intelligence as the ultimate computer, processing every particle's location and momentum, then calculating forward through time with perfect accuracy. Past, present, and future would be equally accessible, like different pages in an already written book. This deterministic vision worked extraordinarily well for building bridges, calculating planetary orbits, and designing machines during the Industrial Revolution. Steam engines operated according to thermodynamic principles derived from Newton's work. Astronomers predicted eclipses decades in advance. Engineers calculated exactly how much steel was needed for railroad trestles spanning vast canyons. The clockwork universe seemed not just elegant, but obviously correct. Nobody suspected that when descending to atomic scales, this entire elegant conceptual edifice would completely collapse into experimental contradictions. The first sign of trouble emerged in the late 19th century when physicists tried to explain how hot objects emit light and heat. This seems like such a simple question. Heat up a piece of metal and it glows. Make it hotter and the glow changes from red to orange to white. What could be complicated about that? A black body is a theoretical object that absorbs all radiation hitting it, like the interior of a metallic cavity heated uniformly. Think of looking into the open door of a blast furnace. When heated, this black body emits radiation in a characteristic spectrum that depends exclusively on its temperature, not the material. The color and intensity of the glow tells you exactly how hot the object is. In 1896, Wilhelm Wien derived a formula describing radiation at short wavelengths well, like visible light and ultraviolet. Lord Rayleigh and James Jeans, using rigorous classical physics, derived another formula that worked only for long wavelengths like infrared. Each formula worked perfectly in its domain, but they predicted completely different things at the boundary between short and long wavelengths. The devastating problem was that the Rayleigh-Jeans formula predicted infinite energy at short wavelengths, which became known as the ultraviolet catastrophe. According to classical physics, any heated object should emit infinite energy instantaneously, which obviously contradicts every possible experimental observation. Your coffee cup should be blindingly bright and infinitely hot. The sun should have vaporized itself in microseconds. Nothing heated should be able to exist stably. Something was profoundly wrong with classical physics, and the problem wasn't a calculation error, but a fundamental conceptual failure. The mathematics was correct, the logic was sound, but the predictions were absurd. It was like discovering that 2 + 2 sometimes equals 5, not because of arithmetic mistakes, but because arithmetic itself broke down under certain conditions. In October 1900, Max Planck presented a formula that combined the Wien and Rayleigh-Jeans regimes into a single mathematically elegant expression. Planck's formula agreed perfectly with all experimental measurements of blackbody radiation at all tested temperatures. Finally, theory matched reality. But the price of this success was steep. To derive this formula, Planck was forced to introduce a radical hypothesis. Energy could only be absorbed or emitted in discrete packets. Imagine trying to fill a bucket with water, but discovering you can only pour specific amounts at once. You can't add a little bit more or a little bit less. Energy came in indivisible chunks, like coins that couldn't be broken into smaller denominations. These energy packets, called quanta, had energy proportional to the frequency of radiation, expressed by the equation E equals h times nu, where h is a constant. The constant h, today called Planck's constant, has the minuscule value of 6.626 times 10 to the -34th joule seconds, explaining why quantization is invisible in everyday life. This number is so small that for ordinary objects, energy appears continuous, just as a beach appears smooth, until you examine individual grains of sand. Planck initially considered quantization a mathematical trick. a technical maneuver to make the calculations work without deep physical meaning. He was like someone who accidentally discovers a secret door while trying to fix a squeaky hinge. He thought he was solving a narrow technical problem in radiation theory, not overturning the foundations of physics. He couldn't imagine that he had just opened an irreparable crack in classical physics that would completely revolutionize our understanding of reality. The implications would eventually touch everything, from the stability of atoms to the operation of smartphone processors to the fundamental nature of measurement itself. On December 14, 1900, Planck presented his complete derivation, a date now considered the official birth of quantum mechanics. Planck told his son Erwin that he had made a discovery as important as Newton's, though he himself didn't fully understand the implications. Like Darwin publishing On the Origin of Species while underestimating how completely it would transform biology, Planck had unleashed forces that would reshape physics, technology, and philosophy. The quantization of energy was only the first shock, and the next would come from a young patent office clerk named Albert Einstein. In 1887, Heinrich Hertz discovered that ultraviolet light shining on metals could make the metal emit electrical sparks, a phenomenon called the photoelectric effect. This seemed straightforward enough at first. Shine light on metal, get electricity out, simple cause and effect. But as physicists dug deeper into the details, they found something that made no sense according to everything they thought they knew about light. Philip Leonard demonstrated in 1902 that light was actually knocking electrons out of the metal, and the energy of these electrons depended on the frequency of the light, not its intensity. Let me help you visualize why this was so baffling. According to classical wave physics, brighter light should produce more energetic electrons, just like bigger ocean waves push objects with more force. If you're standing at the beach and a small wave hits you, it barely moves you, but a massive wave can knock you over completely. Experimentally, increasing the light's intensity only produced more electrons, but each individual electron had the same energy determined by the frequency. It was like discovering that no matter how many garden hoses you aimed at a brick wall, you'd never knock it down. But a single drop of water at the right pitch could shatter it instantly. The analogy breaks down, but you get the idea. Something fundamental was wrong with the wave picture of light. Beyond that, there existed a minimum frequency below which no electron was emitted, regardless of how intense the light applied to the metal became. Picture this absurdity. A giant ocean wave couldn't move a beach ball, while a tiny ripple of a different frequency could launch it skyward instantly. This threshold frequency made absolutely no sense if light was purely a wave. Waves should be able to deliver any amount of energy if you just make them intense enough. In March 1905, Einstein proposed something that seemed even more radical than Planck's energy packets. Einstein suggested that light wasn't just emitted in quanta, as Planck had proposed, but that light itself consisted of discrete particles. Think about this leap. Planck had said energy came in packets, but still thought of light as waves that happened to be quantized. Einstein was claiming light was actually made of particles. These light particles, later called photons, carried energy proportional to their frequency according to the same Planck formula E equals h times nu. A photon of blue light has approximately 3 electron volts of energy, while a photon of red light carries only about 1.8 electron volts. The difference isn't huge in absolute terms, but it's enough to completely change what happens when that photon hits an electron. When a photon strikes an electron in the metal, it transfers all its energy at once, like a billiard ball colliding with another ball. This is crucial. Not gradually, not partially, but completely and instantaneously. The photon doesn't slowly push on the electron like a wave would. It smacks into it like a tiny projectile and disappears, giving up every bit of its energy in that single collision. If the photon's energy exceeds the energy needed to knock the electron out of the metal, called the work function, the electron gets ejected with kinetic energy left over. Think of it like breaking a chain. You need a minimum force to snap the link, but any extra force becomes motion energy once the chain breaks. If the photon's frequency is too low, its energy isn't enough to free the electron, no matter how many weak photons bombard the material. It's exactly like trying to knock down a brick wall. Millions of ping-pong balls won't accomplish what a single bowling ball can do instantly. The ping-pong balls just don't have enough individual energy, regardless of quantity. Similarly, red photons might not have enough energy to knock electrons loose, while blue photons of the same number could create a shower of electrons. Einstein's explanation was mathematically precise and agreed perfectly with all known experimental data about the photoelectric effect. Every measurement, every observation, every careful experiment supported this particle picture of light. But accepting it meant abandoning something physicists had believed for over a century. In 1914, Robert Millikan confirmed Einstein's equation experimentally with extraordinary precision, even though he initially doubted the theory himself. Einstein received the Nobel Prize in Physics in 1921, specifically for his explanation of the photoelectric effect, not for the theory of relativity that made him famous. This tells you something about how revolutionary and well-confirmed this work was. The Nobel Committee recognized that Einstein had fundamentally changed our understanding of light itself. But Einstein's proposal created a profound conceptual problem. Light now seemed to be a wave in some experiments and a particle in others. How could the same phenomenon be two completely different things? This wasn't like matter having different phases. Ice, water, and steam are all still H2O molecules. This was like discovering that the same entity could simultaneously be a baseball and a symphony. In interference and diffraction experiments, light clearly behaves like a wave, producing patterns that water waves also create under similar circumstances. Thomas Young had demonstrated this as early as 1801 with his famous double-slit experiment, where light passing through two slits creates interference patterns. This experiment was considered the definitive proof that light was a wave. When light waves pass through two slits, they overlap on the other side and interfere with each other, creating regions of bright light alternating with darkness. Where the crest of one wave meets the crest of another, the intensity increases through constructive interference, creating bright bands on the screen. Where crests meet troughs, the waves cancel through destructive interference, producing the characteristic dark bands of the interference pattern. This wave behavior had been considered definitive proof that light was a wave, not particles, since the early 19th century. The mathematics worked perfectly, the predictions matched experiments exactly, and the analogy with water waves was compelling. How could discrete particles create the smooth, continuous interference patterns that waves naturally produced? But the photoelectric effect demonstrated that light also behaved like discrete particles carrying quantized energy and definite momentum. You couldn't explain the photoelectric effect with waves, and you couldn't explain interference with particles. Light was neither wave nor particle in the classical sense. It was something fundamentally new that transcended these human mental categories. This wave-particle duality didn't mean that light changed its nature depending on the experiment, but that our conceptual categories were insufficient to describe it. We were like people who had only seen shadows on a wall trying to understand three-dimensional objects. Our language of wave and particle came from our everyday experience with things like water ripples and thrown rocks, but light operated according to rules that everyday experience had never prepared us for. In 1924, a young French physicist named Louis de Broglie made an even more radical proposal in his doctoral thesis at the University of Paris. If light waves could behave like particles, de Broglie asked, why couldn't matter particles behave like waves? This question seems almost inevitable in hindsight, but it took tremendous intellectual courage to ask it. He proposed that all moving matter has an associated wave, with wavelength given by lambda equals h over p, where p is the particle's momentum. Notice that Planck's constant appears again, connecting the world of waves to the world of particles through an elegant and universal mathematical relationship. This wasn't coincidence. It was revealing something fundamental about the structure of reality. For an electron moving at 1% of light speed, the de Broglie wavelength is approximately 9 billionths of an inch, comparable to the size of atoms. This scale is where quantum effects become important, where the wave nature of matter starts to matter for how things behave. For a baseball thrown at 90 miles per hour, the de Broglie wavelength would be absurdly small, about 4 times 10 to the negative 34th inches, completely undetectable. This explains why we don't observe wave behavior in everyday objects. Their wavelengths are trillions of times smaller than atoms. A thrown baseball does have a wave associated with it, but that wave is so incredibly tiny that it has absolutely no measurable effect on the baseball's motion. The wave is there in principle, but irrelevant in practice. De Broglie's hypothesis seemed too speculative, but in 1927, Clinton Davison and Lester Germer demonstrated electron diffraction experimentally using crystals. Electrons, accelerated by 54 volts, were directed at a nickel crystal, and the scattering pattern showed diffraction typical of waves, not the simple reflections expected from particles. The experimentally measured wavelength was 6.5 billionths of an inch, while de Broglie's formula predicted 6.6 billionths of an inch, an impressive agreement that stunned the physics community. Think about what this means. Here were electrons, tiny particles of matter that everyone knew were particles, creating the same interference patterns that light waves made. The mathematics worked almost perfectly. Independently, George Thomson also demonstrated electron diffraction at the same time, using electrons passing through thin metal films. This parallel discovery wasn't unusual in science. When an idea's time has come, multiple researchers often reach the same conclusions simultaneously. But Thomson's story carries a delicious historical irony that perfectly captures the revolution happening in physics. Thomson was the son of J.J. Thomson, who had discovered the electron as a particle in 1897, creating the historical irony of father and son winning Nobel Prizes for opposite aspects of the same electron. The father proved electrons were particles. The son proved electrons were waves. Both were absolutely correct, and both were profoundly incomplete without the other's work. Wave-particle duality wasn't exclusive to light. It was a fundamental property of all matter and energy in the universe. Every electron, every proton, every atom in your body has both particle and wave aspects. You are made of quantum entities that exist as probability clouds until measured, then appear as definite particles when detected. The solid reality you experience is built from fundamentally fuzzy components. Since then, diffraction has been observed with neutrons, entire atoms, and even large molecules like fullerenes containing 60 carbon atoms. In 2019, scientists demonstrated quantum interference with molecules containing more than 2,000 atoms, the largest ever tested in this type of experiment. We're talking about molecules big enough to see with powerful microscopes, yet still displaying the ghostly behavior of quantum waves. The double-slit experiment with individual particles reveals the quantum mystery in its purest and most challenging form for human intuition. This is where classical thinking completely breaks down, where your brain's evolution-trained logic simply cannot make sense of what happens. When electrons are fired one at a time through two slits, each electron hits the detection screen at a specific point, like a particle. Click. One electron detected at position X, nothing strange yet. But over thousands of detections, the individual points accumulate to form exactly the interference pattern expected for waves. Not the pattern you'd expect from particles going through one slit or the other, but the striped pattern of constructive and destructive interference. Each individual electron somehow passes through both slits simultaneously and interferes with itself before being detected as a particle. Let me walk you through why this is so disturbing to classical thinking. Each electron is a single, indivisible particle. It cannot split in half. Yet to create an interference pattern, it must somehow sample both paths through the slits, compare their phases, and land in spots where the waves from both paths interfere constructively. How does a single particle do this? If you place detectors to determine which slit each electron passes through, the interference pattern disappears completely and instantaneously. The electron then behaves like a classical particle, creating only two bands corresponding to the two slits, with no interference between them. The mere possibility of obtaining path information destroys the wave behavior, as if nature actively guards its secrets. This phenomenon doesn't depend on human consciousness observing anything. Any physical interaction that could potentially reveal information about the path causes the same effect. A detector that's turned off doesn't affect the pattern. A detector that's on but not recorded doesn't affect it. Only when information about the path becomes available, even in principle, does the interference vanish. The act of measuring in the quantum world isn't passive like pointing a telescope at a star. Measuring requires physical interaction that inevitably disturbs the system. To detect which slit the electron passed through, we need something to interact with it, and that minimal interaction is enough to destroy the interference. It's like trying to read a book in a dark room by throwing baseballs at it. You might figure out where the book is, but you'll destroy it in the process. In 1927, Werner Heisenberg formalized this fundamental limitation in what became known as the Heisenberg uncertainty principle. This wasn't just about measurement difficulties that better technology could overcome. This was about a fundamental feature of reality itself, built into the mathematical structure of the universe. The principle establishes that it's impossible to know simultaneously the position and momentum of a particle with arbitrary precision as a matter of fundamental physical principle. Mathematically, the product of uncertainties in position and momentum must always be greater than or equal to h bar over 2, where h bar equals Planck's constant divided by 2 pi. Here's a concrete example. If you measure an electron's position with precision of about 4 billionths of an inch, the minimum uncertainty in its momentum will be at least about 1 times 10 to the negative 54th pound-feet per second. These aren't practical measurement errors we might solve with better instruments. This is the universe telling us there are questions that simply don't have answers. This isn't a technological limitation that better instruments could overcome. It's a fundamental property of the mathematical structure of the universe. The uncertainty doesn't mean the particle has definite position and momentum that we simply don't know, like a card face down on a table. The particle genuinely doesn't possess simultaneous precise values for these properties. Asking for them simultaneously is asking a question without a physical answer. Imagine trying to measure a car's position using radar. You fire radio waves that reflect off the car and return to your detector. To determine position precisely, you need waves with short wavelength, which means high frequency and high energy. But high-energy waves, when they reflect off the object, transfer significant momentum, changing the car's velocity in unpredictable and unknown ways. For a macroscopic car, this momentum transfer is negligible compared to the car's total momentum, so the resulting uncertainty is undetectable in practice. The radar photons are like gnats bouncing off a freight train. They barely affect the train's motion. For an electron, however, even a single photon of visible light transfers momentum comparable to the electron's own momentum, disturbing it drastically. Trying to measure more precisely using lower energy photons doesn't work, because low energy photons have long wavelengths and poor spatial resolution. It's like trying to measure the width of a hair with a yardstick. The measuring tool is too coarse for the precision you want. The universe conspires mathematically to prevent you from obtaining complete information about a particle, not out of caprice, but from logical necessity of the theory. The uncertainty principle also applies to other pairs of conjugate variables, like energy and time, following the relation delta E times delta T greater than or equal to h bar over 2. This means that states with very well-defined energy must exist for long periods, while brief states have significant energy uncertainty. It's like a cosmic bookkeeping system where precision in one account requires fuzziness in another. Virtual particles can even briefly violate energy conservation, existing for time so short that the energy uncertainty allows this apparent violation. These quantum fluctuations happen everywhere, all the time, at scales too small and times too brief for direct observation. The vacuum itself seethes with activity, particles popping into and out of existence in a quantum dance at the edge of detectability. The uncertainty principle isn't a defect or limitation of quantum mechanics. It's a direct consequence of the fundamental wave nature of matter. A wave with well-defined wavelength extends infinitely through space, making it impossible to define its position with any precision. Think of a perfect musical note. To have a precise frequency, the sound wave must continue indefinitely. The moment you try to localize it in time by cutting it short, you introduce uncertainty in its frequency. The connection between wavelength and momentum through de Broglie's formula mathematically guarantees that position and momentum cannot both be precise. To understand how atoms function in this new paradigm, we need to completely abandon the familiar image of miniature solar systems. This is perhaps the hardest conceptual leap for anyone learning quantum mechanics. We're deeply attached to the planetary model because it makes intuitive sense. Electrons orbit the nucleus like planets orbit the sun. Simple, elegant, and completely wrong. In Bohr's model from 1913, electrons orbited the nucleus in defined circles, like planets orbiting the sun on minuscule and elegant scales. This model explained the hydrogen spectrum beautifully, predicting exactly which colors of light hydrogen atoms would emit when excited. For a while, it seemed like atomic structure was solved. But the model failed for more complex atoms and directly contradicted the newly discovered uncertainty principle. If an electron followed a definite circular orbit, we would know its position and momentum simultaneously with precision, violating Heisenberg's principle. An electron in orbit has a definite position along its circular path and a definite momentum in the direction of motion. But the uncertainty principle says this is impossible. Something had to give, and it was our mental picture of orbits. Quantum mechanics replaced definite orbits with orbitals, which are regions of space where there's significant probability of finding the electron. Not paths the electron follows, but zones where it might be detected if you look for it. The electron doesn't travel a circular path. It exists as a probability cloud distributed around the nucleus in 3 dimensions. This cloud is denser near the nucleus, indicating higher probability of finding the electron there, and gradually diminishes with distance. Picture a cloud of gnats around a picnic table, denser near the food, sparser farther away, but with no definite boundary. The mathematical form of these clouds is determined by the Schrödinger equation, published by Erwin Schrödinger in 1926 as the fundamental equation of quantum mechanics. The Schrödinger equation is to quantum mechanics what Newton's F equals ma is to classical mechanics, the fundamental law of motion. But instead of predicting definite trajectories like Newton's laws, Schrödinger's equation predicts probabilities. Instead of telling you where a particle will be, it tells you where you might find it and with what likelihood. The solutions to this equation are wave functions, represented by the Greek letter psi, which contain all possible information about the quantum state of a system. Think of the wave function as the complete quantum blueprint of a particle's possibilities. It doesn't tell you what will happen, but it tells you everything that could happen and how likely each possibility is. The square of the absolute value of the wave function gives the probability density of finding the particle at each point in space. Where the wave function is large, you're likely to detect the particle. Where it's small, detection is unlikely. Where it's zero, you'll never find the particle. The wave function is like a three-dimensional map of possibilities. The probabilistic interpretation was proposed by Max Born in 1926, earning him the Nobel Prize in Physics in 1954 for this fundamental contribution. Initially, Schrödinger thought the wave function represented the actual particle spread out through space, like a diffuse cloud of matter, but experiments showed that when measured, particles always appeared at specific points, not spread out. The wave function collapsed instantaneously from a distributed probability to a definite detection. This collapse of the wave function remains one of the most debated aspects of quantum mechanics, generating radically different philosophical interpretations. What does it mean for a probability wave to suddenly become a definite particle? And how does this happen? In the Copenhagen interpretation, developed by Bohr and Heisenberg, the wave function represents our knowledge of the system, not an independent physical reality. Before measurement, it makes no sense to ask where the particle is. It genuinely doesn't have a definite position until a measurement forces it to have one. This isn't ignorance on our part. The particle actually doesn't possess the property we're asking about. Measurement doesn't reveal a pre-existing property. It participates in creating the measured property through interaction between system and apparatus. Think about this carefully. The act of measurement brings the measured property into existence. Before measurement, asking, "Where is the electron?" is like asking, "What's the color of Wednesday?" The question assumes something that doesn't exist. Einstein detested this interpretation, expressing his objection in the famous phrase, "God does not play dice with the universe," referring to fundamental randomness. Einstein believed the universe had to be deterministic at its foundation. Quantum randomness, in his view, meant the theory was incomplete. Hidden variables must determine outcomes that quantum mechanics could only describe statistically. Bohr responded that Einstein shouldn't tell God what to do, defending that quantum randomness was genuine, not the result of ignorance. For Bohr, the universe really was probabilistic at its foundation. There were no hidden clockwork mechanisms determining outcomes in advance. The universe genuinely left certain questions unanswered until measurement forced an answer. The debate between Einstein and Bohr about the foundations of quantum mechanics lasted decades, profoundly shaping theoretical physics development. It wasn't just academic disagreement. It was about the fundamental nature of reality itself. Is the universe deterministic or probabilistic? Do properties exist independently of measurement? Can we describe nature objectively, or are we always part of what we describe? In 1935, Einstein, Boris Podolsky, and Nathan Rosen published the famous EPR paper, arguing that quantum mechanics was incomplete as a description of reality. Their argument involved two particles that had interacted and then separated, remaining correlated in ways Einstein considered paradoxical. This became known as the EPR paradox. If two particles are correlated, measuring one property of one particle instantaneously determines the corresponding property of the other, regardless of distance. Measure the first particle's spin as up, and you instantly know the second particle's spin is down, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance, arguing that properties must be predetermined by unknown hidden variables. Bohr responded that the EPR argument failed because it assumed we can talk about particle properties independently of the experimental arrangement used to measure them. For Bohr, the particles formed a single indivisible system, and discussing separate local properties was philosophically unjustifiable in the quantum context. You can't separate the system from how you choose to examine it. The debate seemed purely philosophical until 1964, when John Bell derived mathematical inequalities that allowed experimental testing of the question. Bell's inequalities showed that any local hidden variable theory would make different predictions from quantum mechanics in certain specific experiments. Finally, philosophy could be settled by measurement. Starting in the 1970s, and especially in Alain Aspect's experiments in 1982, experimental tests consistently confirmed quantum mechanics predictions. Quantum correlations violate Bell's inequalities, demonstrating that nature cannot be described by local realistic hidden variable theories. Einstein's intuitions about hidden variables were wrong. The universe really is non-local and probabilistic. Aspect John Clauser and Anton Zeilinger received the Nobel Prize in Physics in 2022 for these experiments that established quantum correlations beyond doubt. Their work proved that quantum mechanics isn't just a useful calculational tool, but an accurate description of reality's strange, non-local nature. The universe really does behave in ways that violate our classical intuitions. The result doesn't mean information travels faster than light. The correlations can't be used to send signals, preserving causality, but it does mean that quantum reality is genuinely non-local in some deep sense, connecting distant parts of the universe in ways without classical analogy. Two particles that have once interacted remain connected in a fundamental way, no matter how far apart they travel. The universe maintains invisible threads between them that somehow coordinate their behavior without exchanging signals. Returning to atomic structure, atomic orbitals have shapes determined by quantum numbers that emerge naturally from solutions to the Schrödinger equation. These aren't arbitrary mathematical constructs. They represent the actual three-dimensional probability distributions where electrons can be found. The principal quantum number n determines the energy and general size of the orbital, with positive integer values 1, 2, 3, and so on. Think of these quantum numbers as nature's filing system. The principal quantum number n is like the floor of a building. Higher floors have more energy and are farther from the nucleus. The angular momentum quantum number L determines the orbital's shape, varying from 0 up to n-1 for each value of n. This is like different room shapes on each floor. Orbitals with L equals 0 are called s orbitals and have spherical shape, like perfect bubbles centered on the nucleus. Orbitals with L equals 1 are called p orbitals and have dumbbell shapes with two lobes, like balloons pinched in the middle. The electron probability is concentrated in these lobes, with zero probability at the pinch point between them. Orbitals with higher angular momentum have progressively more complex shapes. D orbitals, where L equals 2, and F orbitals, where L equals 3, have multiple lobes and characteristic angular nodes where the probability drops to zero. These complex shapes arise naturally from the wave mathematics. They're not arbitrary design choices, but inevitable consequences of wave behavior in 3 dimensions. The magnetic quantum number m determines the orbital's spatial orientation, varying from negative L to positive L in increments of 1. For p orbitals, you can have 3 orientations, one pointing along each axis in 3-dimensional space. For d orbitals, you get 5 different orientations. Each orientation represents a different way the same basic shape can be positioned in space. Finally, electron spin adds one more quantum number, which can be +1/2 or -1/2, representing 2 possible intrinsic orientations. Spin isn't actually spinning in the classical sense. It's an intrinsic quantum property with no classical analogy. But the mathematics treats it like an internal compass that can point in one of 2 directions. The Pauli exclusion principle, formulated in 1925, establishes that no 2 electrons in the same atom can have identical sets of all 4 quantum numbers. This seemingly simple rule has profound consequences. It means each orbital can hold at most 2 electrons, and they must have opposite spins. It's like a cosmic hotel where each room has 2 beds, but the occupants must have opposite orientations. This principle explains the structure of the periodic table. Electrons fill orbitals in order of increasing energy, with no more than 2 per orbital and opposite spins. The first shell holds 2 electrons in the s orbital, the second shell holds 8, 2 in the s orbital and 6 in the 3p orbitals. The third shell can hold 18, and so on. Without the Pauli principle, all electrons would collapse into the lowest energy orbital, and chemistry as we know it would be completely impossible. Every atom would be a miniature hydrogen, with all electrons crowded into the same space. There would be no diversity of elements, no different chemical properties, no molecules. The entire rich tapestry of chemistry depends on this quantum rule, forcing electrons into different energy levels. The diversity of elements, molecules, and materials composing the universe depends fundamentally on this apparently simple but profoundly consequential quantum rule. Carbon has its unique bonding properties because its electrons are arranged in specific orbitals. Silicon behaves differently because its electrons occupy different energy levels. The entire periodic table emerges from quantum mechanics applied to many electron atoms. Quantum superposition is another concept that radically challenges classical intuition about how physical systems behave before being observed. A quantum system can exist simultaneously in multiple states until measurement forces the system to choose one of the possible states. This isn't like being uncertain about a coin flip before looking. The system genuinely exists in multiple states at once. Schrödinger's cat is the most famous didactic example. A cat in a box is simultaneously alive and dead until someone opens the box and observes. Schrödinger proposed this thought experiment in 1935 precisely to show the absurdity of applying quantum superposition to macroscopic everyday objects. He was trying to demonstrate how ridiculous the quantum world seemed when extended to familiar scales. For individual particles, however, superposition is experimentally verified. Electrons, photons, and even molecules exist in superpositions before measurement. The absurdity Schrödinger highlighted doesn't invalidate quantum mechanics. It reveals the boundary between quantum and classical worlds. The transition between the quantum world of superpositions and the classical world of definite states remains one of physics' most important open problems. Quantum decoherence offers partial explanation. Interactions with the environment destroy superpositions on extremely short timescales for macroscopic objects. A molecule in air undergoes about 100 trillion collisions per second, and each collision tends to destroy delicate quantum superpositions almost instantaneously. The environment acts like a continuous measurement apparatus. This is why we don't observe cats in superposition. The environment continuously measures the cat, collapsing any incipient superposition before it can establish itself. Every photon hitting the cat, every air molecule bouncing off it, every vibration through the floor acts as a measurement that forces definite states. Classical behavior emerges from quantum foundations through environmental interaction. But for systems well isolated from the environment, like atoms in traps at temperatures within degrees of absolute zero, superpositions can be maintained and studied. Modern experiments have created superpositions in increasingly large systems, including Schrödinger cats of thousands of atoms in superposed states. We're pushing the boundary between quantum and classical worlds to larger and larger scales. Quantum computing exploits exactly this ability of qubits to exist in superposition of 0 and 1 simultaneously, processing multiple possibilities in parallel. While classical bits are definitively 0 or 1, qubits can be combinations of both, with probabilities of collapsing to each value when measured. This is where the computational power comes from. 2 qubits can be in superposition of 4 states, 0, 0, 0, 1, 1, 0, 1, 1. 3 qubits can represent 8 states, and n qubits can represent 2 to the nth states simultaneously. 50 qubits in superposition represent 2 to the 50th states, more than a quadrillion, processed in some sense simultaneously through quantum parallelism. Quantum algorithms like Shor's can factor large numbers exponentially faster than classical algorithms, threatening current cryptography. Grover's algorithm searches unstructured databases with quadratic acceleration over classical methods, demonstrating practical quantum advantage. But maintaining qubits in coherent superposition, long enough for useful computations, remains the greatest technical challenge for practical quantum computers. Despite all this conceptual strangeness, quantum mechanics is the most precisely tested and confirmed physical theory in human science history. Quantum electrodynamics predictions agree with experiments to 12 decimal places, precision comparable to measuring the Earth-Moon distance with error of a hair's width. The anomalous magnetic moment of the electron was calculated theoretically as 2.00231930436256 and measured experimentally as 2.00231930436146. Extraordinary agreement. All modern technology depends fundamentally on quantum principles, from smartphones to medical diagnostic imaging equipment. Transistors, the basic components of all electronic circuits, function based on quantum properties of semiconductors like silicon and germanium. The behavior of electrons in semiconductors, including energy bands and tunneling, is purely quantum and cannot be explained classically. In a classical world, electrons in silicon would behave like tiny balls rolling around randomly. But quantum mechanics reveals that electrons occupy specific energy bands, with forbidden gaps between them. This band structure is what makes semiconductors useful for electronics. Think about what's happening inside your smartphone right now. A single modern processor chip contains more than 50 billion transistors, each one operating according to principles that Einstein and Bohr debated intensely. Every time you send a text, stream a video, or run an app, you're relying on quantum mechanics billions of times per second. The device in your pocket is essentially a quantum mechanical computer, though we don't usually think of it that way. Each transistor works by controlling the flow of electrons through quantum mechanical tunneling and band gap engineering. When you press a key on your phone, you're triggering cascades of quantum events through semiconductor materials whose properties were designed using the Schrödinger equation. The same equation that describes hydrogen atom orbitals also governs the electron flow in your phone's processor. Lasers are another ubiquitous example that surrounds us daily. Stimulated emission, the physical principle behind lasers, was first described theoretically by Einstein in 1917 using quantum theory. When a photon with the right energy hits an excited atom, it can stimulate emission of an identical photon, a process impossible to explain classically. The atom doesn't just randomly emit light, it's triggered by the first photon to emit a second photon with exactly the same frequency, direction, and phase. This stimulated emission creates the coherent light that makes lasers so useful. DVD players, fiber optic communication carrying internet data across oceans, eye surgery correcting vision, industrial cutting and welding, military ranging systems, and thousands of other applications depend on lasers and therefore on quantum physics. That laser pointer you use for presentations operates on the same quantum principles that Einstein first described over a century ago. The barcode scanner at the grocery store uses laser light to read product codes. The checkout process that seems so mundane actually depends on quantum mechanical coherent light interacting with printed patterns. Your internet connection, whether fiber optic or wireless, relies on quantum mechanical devices to encode, transmit, and decode information. Every photo you upload, every video you stream, every message you send travels through quantum mechanical systems. Nuclear magnetic resonance, used in hospital MRI scanners, exploits the quantum spin of atomic nuclei to create detailed tissue images. The hydrogen nuclei in your body, which make up a significant fraction of your mass through water molecules, align themselves in strong magnetic fields and respond to radio frequency pulses in purely quantum ways. The spin-angular momentum of protons has no classical analogy. It's an intrinsic quantum property. When an MRI machine surrounds you with magnetic fields up to 60,000 times stronger than Earth's magnetic field, it's forcing the quantum spins in your body to align like tiny compass needles. Radio frequency pulses then flip these spins, and the machine detects the quantum mechanical precession as the spins relax back to alignment. Different tissues have different relaxation times, creating the contrast in MRI images. Without quantum understanding of nuclear spin, MRI would be impossible, and millions of non-invasive medical diagnoses would never have been performed. Brain tumors detected without surgery, torn ligaments visualized without cutting, internal organ function assessed without invasion. All depends on our mastery of quantum spin physics applied to medical imaging. LEDs illuminating your home and solar panels on rooftops function through the photovoltaic effect, intimately related to the photoelectric effect Einstein explained quantum mechanically in 1905. When sunlight photons strike semiconductor materials in solar panels, they create electron-hole pairs that generate electric current through quantum processes. The clean energy revolution depends fundamentally on our understanding of quantum mechanics applied to materials science. In an LED, electric current excites electrons to higher energy levels in semiconductor crystals. When these electrons fall back to lower levels, they emit photons with energy exactly equal to the band gap difference. The color of the light depends on the quantum mechanical energy levels in the semiconductor material. Blue LEDs were so difficult to develop that their inventors won Nobel Prizes in 2014. GPS satellites orbiting 12,400 miles above your head depend on atomic clocks, whose extreme precision comes from specific quantum transitions in cesium or rubidium atoms. The transition frequency of cesium-133, exactly 9,192,631,770 Hz, has officially defined the second in the International System of Units since 1967. This quantum precision is essential because GPS works by measuring tiny time differences between signals from multiple satellites. Without quantum atomic precision, GPS satellites would have positioning errors measured in miles instead of feet. Your phone's map application, navigation systems in cars and airplanes, precision agriculture, earthquake monitoring, and countless other location-dependent technologies all rely on quantum mechanical timekeeping. Scanning tunneling microscopes exploit quantum tunneling, where particles traverse energy barriers that would be classically insurmountable. A classical particle would bounce off a barrier if it didn't have enough energy to overcome it, like a ball rolling against a steep hill. Quantum mechanically, the wave function penetrates into the barrier and has non-zero probability on the other side, allowing particles to appear beyond barriers they shouldn't classically cross. These microscopes can image individual atoms on surfaces by measuring tunneling current between a sharp probe tip and the sample. The tunneling current depends exponentially on the distance, providing incredible sensitivity to atomic scale features. Scientists use quantum tunneling to manipulate individual atoms, building structures atom by atom and exploring matter at its most fundamental level. Quantum tunneling is essential in nuclear reactions in the Sun. Protons in the solar core must overcome enormous electrical repulsion to get close enough for nuclear fusion. The Sun's core temperature is about 27 million degrees Fahrenheit, incredibly hot, but not hot enough for classical physics to explain observed fusion rates. Quantum tunneling allows protons to penetrate the electrical barrier even without sufficient classical energy. Without tunneling, the Sun would be too cool for nuclear fusion, and life on Earth would never have existed to contemplate these questions. Every photon warming your face, every plant growing through photosynthesis, every weather pattern driven by solar heating depends on quantum mechanical tunneling in stellar cores. The energy source for all life on Earth is fundamentally quantum mechanical. The structure of all chemistry emerges directly from quantum mechanics applied to electrons in atoms and molecules interacting electromagnetically. Chemical bonds are purely quantum phenomena. Electrons shared between atoms exist in molecular orbitals that are solutions to the Schrödinger equation. The shapes of water molecules, DNA, and proteins that sustain life derive from orbital geometries and bonding energies determined quantum mechanically. Consider the water molecule. Its bent shape, with hydrogen atoms at a specific angle to the oxygen, results from quantum mechanical hybridization of atomic orbitals. This shape determines water's unique properties, its ability to dissolve substances, its expansion when freezing, its role in biological systems. Every biological process in your body depends on molecular shapes determined by quantum mechanics. DNA's double helix structure emerges from quantum mechanical bonding between base pairs. The hydrogen bonds holding the two strands together, the stacking interactions between bases, the backbone phosphate groups, all governed by quantum mechanical electron distributions. Protein folding, enzyme catalysis, cellular respiration, photosynthesis, every aspect of biochemistry is quantum mechanics in action. Even atomic stability is a quantum phenomenon. Classically, accelerated electrons in orbit would radiate energy continuously and spiral into the nucleus in trillionths of a second. Quantization of energy levels prevents this collapse, ensuring atoms exist stably long enough to form complex universes. Without quantum mechanics, matter as we know it couldn't exist. There would be no atoms, no molecules, no chemistry, no life. Quantum physics isn't just a theory about small particles. It's the foundation upon which all observable material reality is constructed. Every experiment ever performed, every technology ever built, every observation ever made confirms that the universe operates according to quantum rules fundamentally. The classical world we experience emerges from quantum foundations, not the other way around. The strangeness we feel confronting quantum mechanics isn't a flaw in the theory, but inadequacy of intuitions shaped by experiences on irrelevant scales. When Einstein said he didn't believe God played dice, he was expressing psychological discomfort, not making a valid physical objection. His human intuitions, like ours, were shaped by experiences with objects millions of times larger than atoms. Quantum randomness isn't like not knowing a dice result before rolling. It's more fundamental, as if the result doesn't exist before the roll. This indeterminacy doesn't mean quantum physics is incomplete, or that undiscovered hidden variables would restore classical determinism. Bell's theorems and subsequent experiments conclusively demonstrated that no local deterministic theory can reproduce verified quantum predictions. We must accept that the universe genuinely doesn't specify certain results until appropriate interactions occur, creating facts through the measurement process itself. This doesn't mean conscious observers create reality. Physical interactions with any sufficiently complex system cause identical collapses. An automatic detector without human consciousness collapses wave functions as effectively as a physicist observing. Consciousness has no special privileged role. The many worlds interpretation proposes that wave functions never collapse. All possibilities realize themselves in parallel branches of universal reality. In this view, when measuring an electron, the universe branches. In one branch, you observe spin up. In another branch, you observe spin down. This interpretation eliminates the mysterious collapse, but introduces infinitely many parallel universes continuously proliferating, which some consider ontologically extravagant beyond reason. Every quantum measurement splits reality into multiple branches, creating countless versions of you experiencing different outcomes. Some find this conceptually elegant because it preserves the mathematical purity of quantum mechanics without arbitrary wave function collapse. The Bohm interpretation proposes that particles always have definite positions, guided by a pilot wave that obeys the Schrödinger equation. In this deterministic but explicitly non-local approach, the pilot wave connects distant particles instantaneously in ways that violate common spatial intuition. Hidden variables determine all outcomes, but these variables are fundamentally unknowable and non-local, creating what Bohm called quantum potential. Different interpretations agree on all experimental predictions, but differ philosophically about what the mathematics means metaphysically about reality. For practical purposes, physicists generally adopt the pragmatic attitude of shut up and calculate, focusing on verifiable predictions instead of metaphysics. This approach has worked extraordinarily well for technological applications and experimental design. But interpretative questions matter for fundamental physics research. Different intuitions guide different research programs investigating quantum gravity and cosmology. How you think about wave function collapse affects how you approach the measurement problem. Whether you believe in many worlds or pilot waves influences how you investigate the quantum to classical transition. Philosophy and physics remain intertwined at the frontiers of knowledge. Standard quantum mechanics and Einstein's general relativity are both extraordinarily well-confirmed theories, but they're mathematically incompatible in certain situations. Within black holes and during the Big Bang, where extreme gravity meets quantum scales, no existing theory provides reliable, consistent predictions. This represents one of the most profound problems in modern physics. Inside black holes, where matter compresses to infinite density and space-time curvature becomes infinite, quantum effects should become important. But general relativity breaks down at singularities, and quantum field theory assumes a fixed space-time background. Neither theory can handle the extreme conditions where both quantum mechanics and gravity are essential simultaneously. Theories of quantum gravity like string theory and loop quantum gravity attempt to reconcile quantum mechanics and relativity, but neither is completely developed or experimentally confirmed. String theory requires extra spatial dimensions and energy scales far beyond current experimental reach. Loop quantum gravity quantizes space-time itself, but struggles to reproduce general relativity in appropriate limits. The Planck scale, where quantum gravitational effects would be important, involves distances of about 4 × 10 to the -34 inches, trillions of times smaller than protons. At these scales, space-time itself might become granular or foam-like, with quantum fluctuations creating and destroying virtual black holes continuously. Space and time might lose their familiar meanings. Accessing this scale experimentally would require energies incomprehensibly larger than any conceivable particle accelerator with known technology. To probe Planck-scale physics directly would require a particle accelerator larger than the solar system, operating at energies equivalent to entire stellar outputs. Such experiments remain far beyond human technological capabilities for the foreseeable future. This doesn't mean fundamental physics is finished. Many phenomena remain poorly understood, and active research continues on multiple fronts. Dark matter, comprising about 27% of the universe, doesn't interact electromagnetically, and its fundamental nature remains unknown, despite decades of intensive searching. We know it exists through gravitational effects on visible matter, but its identity remains mysterious. Dark energy, responsible for the universe's accelerating expansion, comprises about 68% of the total energy content and is even more mysterious than dark matter. We've measured its effects on cosmic expansion with increasing precision, but we have no compelling theoretical understanding of what it actually is. It could be a cosmological constant, a dynamic field, or something entirely unexpected. Quantum mechanics may need extensions or modifications to explain these phenomena completely and incorporate gravity into a unified, coherent theory. The history of physics shows repeatedly that extraordinarily successful theories eventually encounter domains where they're superseded by more comprehensive frameworks. This doesn't invalidate the earlier theories, but reveals their limitations and scope of applicability. Newtonian mechanics was replaced by relativity and quantum mechanics, which will presumably be incorporated into some even more fundamental future theory. But any future theory will have to reproduce quantum predictions in their domains of applicability, just as relativity reproduces Newtonian predictions in appropriate limits. Scientific theories don't disappear. They become special cases of more general frameworks. Quantum strangeness won't disappear with future theories. Any theory that agrees with experiments will have to incorporate the strangeness we've already observed. Superposition, entanglement, and indeterminacy aren't artifacts of imperfect theories. They're experimentally verified characteristics that any valid theory must contain. The weirdness is in nature itself, not in our descriptions of it. The deepest lesson of quantum mechanics is perhaps epistemological. There are fundamental limits to what can be known, not just to what we currently know. It's not that we need better instruments. Nature itself doesn't contain the information we naively imagined it should specify completely. Questions like, where exactly was the electron before I measured it, may simply have no answers, not because we don't know, but because there is no answer. This represents a radical philosophical shift from Laplacian determinism, where the universe's present state would completely determine all future and past events. The quantum universe is more like a game where rules determine outcome probabilities, but specific results aren't predetermined until they occur. The universe leaves certain questions genuinely open until interactions force definite answers. This randomness isn't chaos or disorder. The probabilities are precisely calculable, and statistical distributions are completely mathematically predictable. Quantum mechanics is deterministic at the wave function level. Indeterminacy appears only when translating wave functions into measurement results. We can predict the shape of probability distributions perfectly while remaining ignorant of individual outcomes. A physicist, knowing the complete wave function, can calculate exactly the probability of each possible result, even while being unable to predict which specific result will occur. This is the maximum precision nature permits, and no amount of intelligence or information can exceed this fundamental limit imposed by the universe itself. The limitation isn't in our theories or instruments. It's built into reality's structure. Humanity has discovered that the universe doesn't operate according to intuitions developed for survival on African savannas millions of years ago. This isn't human failure. It's simply the result of our biological origins in environments where quantum physics was completely irrelevant to survival. Our ancestors needed to track prey, avoid predators, and navigate landscapes, not understand electron behavior. The ability to transcend these intuitions and understand reality through mathematics and experiment represents one of the greatest intellectual achievements of our species. No other animal develops partial differential equations to describe system behavior that their senses could never detect directly. The capacity to think beyond evolved intuitions demonstrates the remarkable flexibility of human cognition when properly applied. Science allows minds shaped by ancient evolutionary pressures to comprehend reality domains completely inaccessible to direct everyday experience. We can understand neutron stars, quantum tunneling, and cosmic expansion, not because we evolved to grasp these concepts, but because we developed mathematical and experimental methods that transcend biological limitations. The early 20th century physicists weren't more intelligent than previous generations. They had new experimental data that forced conceptual revision. Planck, Einstein, Bohr, Heisenberg, Schrödinger, Dirac and others collectively built a theoretical edifice that revolutionized our fundamental understanding of nature. Each contributed essential pieces, frequently disagreeing intensely about interpretation while agreeing on mathematically verifiable experimental predictions. The genius wasn't individual brilliance, but collaborative construction of a conceptual framework that could accommodate unprecedented experimental findings. The Bohr-Einstein debate, lasting decades, exemplifies how scientists can disagree profoundly about meaning while converging on practical results. Einstein couldn't accept quantum indeterminacy and spent years trying to prove quantum mechanics incomplete. Bohr defended the probabilistic interpretation and the complementarity principle. Their disagreement was philosophical, not mathematical. Both used the same equations and got the same experimental predictions. Einstein was wrong about quantum mechanics being incomplete, but his objections were productive, forcing clarification of concepts and eventually leading to Bell's theorem. Science progresses not just through correct insights, but through productive errors that push understanding forward. Einstein's mistakes about quantum mechanics led to deeper insights about non-locality and the nature of physical reality. Scientific progress frequently comes from creative tensions between different visions, not from premature consensus or excessive intellectual conformity. The quantum revolution emerged from debates, disagreements, and challenges to established ideas. If everyone had immediately accepted the first quantum hypothesis without questioning, the theory would never have developed its current sophisticated form. Today, a century after quantum mechanics formulation, we still debate interpretive questions while routinely applying the theory to mundane technologies. Your smartphone works because engineers know how to apply quantum mechanics to semiconductors, regardless of philosophical questions about what the theory means. Practical application and philosophical understanding can proceed independently. The extraordinary practical utility of the theory coexists with deep philosophical mystery about what it tells us regarding reality's ultimate nature. We can build quantum computers, design laser systems, and create new materials using quantum principles while remaining uncertain about what quantum mechanics really means. This separation of practical and philosophical understanding is unusual in science, but unavoidable with quantum mechanics. Feynman famously said, "Nobody understands quantum mechanics," meaning nobody has comfortable intuition for it like we have for classical physics. But we understand in the sense of knowing how to apply it. We know how to calculate, predict, build technologies, and verify experimentally with extraordinary and consistent precision. Understanding doesn't require intuitive comfort. Intuitive comfort may never come. Future generations might simply accept quantum strangeness as natural, without expecting the universe to make classical sense. Children growing up with quantum computers might find superposition as intuitive as previous generations found Newtonian mechanics simply through familiarity. What seems impossible to us might seem obvious to them. Intuition isn't biologically fixed. It's shaped by experience, education, and conceptual tools available in each historical epoch. Medieval scholars couldn't intuitively grasp planetary motion because they lacked appropriate mathematical frameworks. Similarly, we struggle with quantum concepts because our intuitions developed in classical environments. But intuitions can evolve with exposure and education. What seems impossible or paradoxical to one generation can seem obvious or trivial to subsequent generations with different education and experience. Heavier-than-air flight seemed impossible until the Wright brothers demonstrated it. Continental drift seemed absurd until plate tectonics explained it. Quantum mechanics seems strange now, but may seem natural to future physicists trained from childhood in quantum thinking. Quantum physics isn't strange because the universe is fundamentally bizarre or irrational. It seems strange because our expectations were inappropriate. We expected fundamental reality to resemble tables, billiard balls, and clocks because those were our formative and limited experiences. We extrapolated from familiar scales to unfamiliar ones, assuming similarity where none existed. The universe has no obligation to seem familiar or comforting. It simply is what it is, independent of our psychological desires. Our expectations about how reality should behave were shaped by evolutionary pressures completely unrelated to understanding atomic-scale phenomena. The universe doesn't care what seems reasonable to creatures evolved for survival on African savannas. Quantum mechanics teaches us humility. We're not the center of the universe, or privileged to understand it intuitively just by existing within it. But it also teaches us about human mental power. We can transcend evolved intuitions and build knowledge about domains completely alien to direct experience. This represents a triumph of reason over biological limitation. This is perhaps science's greatest achievement, showing that reality is comprehensible even when not intuitive, accessible even when not familiar. We can understand neutron stars without visiting them, comprehend quantum mechanics without shrinking to atomic size, and grasp cosmic evolution without living for billions of years. Mathematics and experiment allow minds to transcend their physical limitations. Mathematics serves as a universal language that precisely describes what everyday words fail to capture adequately or consistently. Terms like wave and particle break down at quantum scales because they derive from macroscopic experience. Mathematical equations express quantum behavior precisely without misleading classical analogies. The mathematics is the physics, not a description of it. Quantum equations aren't metaphors or approximations. They're exact descriptions of how nature behaves, verified trillions of times in experiments. When Schrödinger's equation predicts a probability distribution, repeated experiments reproduce exactly that distribution, without known exceptions. The mathematical precision is extraordinary and unprecedented in physics history. No theory in physics history has been so completely and precisely confirmed as quantum mechanics in its tested domains of applicability. Every prediction has been verified, every application has worked, every technological implementation has succeeded. The theory's track record of success is unmatched. If quantum mechanics is wrong, it's the most successful wrong theory ever conceived. If there's a simple message after a century of quantum mechanics, it's this: reality is more subtle than it appears, but completely accessible to investigation. The universe doesn't hide its secrets. It just doesn't present them in formats that evolved primate brains would expect or naturally prefer. The secrets are there, waiting for minds equipped with appropriate tools. With mathematics, experimentation, and persistence, we can peel back reality's layers and find deep structures governing everything that exists materially. Quantum mechanics revealed the first layer beneath classical appearances. What deeper layers await discovery? What structures lie beneath quantum mechanics itself? The journey of understanding continues. Quantum physics isn't the end of comprehension, but a gateway to even deeper domains that future generations will explore with tools not yet invented. The unification of quantum mechanics with gravity, understanding of dark matter and dark energy, and other open questions await future significant discoveries. Each generation builds on previous foundations while pushing boundaries further. Each answer generates new questions. Each solved mystery reveals deeper mysteries, waiting for curious and persistent minds to investigate them. The universe seems designed to reward intellectual effort with ever deeper understanding, while always maintaining horizons beyond current knowledge. This process of discovery appears inexhaustible. The universe isn't strange. Its fundamental physics is completely consistent and mathematically elegant, just different from our provincial expectations. We're intermediate-scale creatures living on a medium-sized planet, orbiting an ordinary star in a typical galaxy within the vast cosmos. Our perspective is inevitably limited by our cosmic position, and expanding that perspective requires abandoning prejudices about how reality should function. Quantum physics is an invitation to see the universe as it is, not as we would like it to be or expected it to be based on limited experience. This invitation, though challenging, is also liberating. We're free from comfortable illusions and open to wonders that naivety never would imagine. Quantum reality doesn't need our approval or intuitive understanding to function. It operates perfectly well, independent of conscious observers. The equations of quantum mechanics describe how particles behave whether humans are watching or not, whether we understand the implications or not, whether we find the results comfortable or disturbing. The universe doesn't require our philosophical consent to operate according to its fundamental principles. Billions of years before humans existed, atoms obeyed quantum mechanics. Stars formed through quantum processes, planets coalesced according to quantum-governed chemical bonding, and complex molecules assembled following quantum mechanical rules. The early Earth's atmosphere developed through quantum chemistry, organic compounds formed via quantum interactions, and the first self-replicating molecules emerged from quantum mechanical molecular dynamics. Billions of years from now, atoms will continue obeying quantum mechanics with or without witnesses. Long after human civilization has passed into cosmic history, electrons will still exhibit wave-particle duality. Quantum entanglement will still connect distant particles, and the uncertainty principle will still limit simultaneous knowledge of conjugate variables. These aren't human discoveries about reality, they are reality. Our capacity to discover these laws is circumstantial and recent. The laws themselves are eternal and universal, completely transcending human existence. We've been aware of quantum mechanics for barely a century, while these principles have governed reality for nearly 14 billion years since the Big Bang. We're latecomers to a cosmic story that was already unfolding according to quantum rules long before the first human ancestor learned to use tools. When contemplating quantum physics, we contemplate structures that sustain the existence of everything, including the brains that make contemplation possible. The calcium ions flowing through your neurons, the sodium and potassium channels regulating nerve impulses, the molecular machinery of consciousness itself, all governed by quantum mechanical principles. There's a certain vertigo in realizing that the matter composing thoughts is subject to laws that those very thoughts discover and describe mathematically. We are the universe contemplating itself, quantum particles organized into structures capable of discovering the laws governing quantum particles. Carbon atoms forged in stellar cores, arranged in neural networks, processing information about the quantum behavior of carbon atoms. This recursive self-awareness represents something unprecedented in the known universe. Matter has become sufficiently complex to understand its own fundamental behavior. This cosmic self-awareness, mediated by quantum physics, is possibly unique in the observable universe, or perhaps common, awaiting discovery of alien intelligences. We don't yet know whether consciousness is rare or abundant in the cosmos, but either possibility is profound. If we're alone, then the universe's self-understanding depends entirely on us. If we're not alone, then self-awareness might be a natural consequence of sufficient complexity anywhere in the cosmos. Regardless of whether we're alone or not, the journey of understanding that quantum physics represents is one of mind's greatest enterprises. From Planck confronting blackbody radiation in 1900 to modern experiments with quantum entanglement spanning continents, each generation has advanced fundamental comprehension a little further. The cumulative progress over just 1 century is staggering when you consider where we started. Planck initially thought quantization was a mathematical trick. Einstein didn't fully grasp the implications of his photon hypothesis. Bohr's atomic model was a stepping stone to something far more sophisticated. Heisenberg discovered uncertainty relations while struggling with matrix mechanics. Schrödinger wrote his equation while trying to understand de Broglie waves. Each breakthrough seemed incremental at the time, but collectively revolutionized our worldview. Mistakes were made, false paths were followed, intense debates occurred, but cumulative progress is undeniable and inspiring to contemplate. Science works not because scientists are infallible, but because the method corrects errors through experimental verification and peer review. Individual brilliance matters, but the collective process of testing, refining, and advancing understanding matters more. Truth emerges from the community's efforts, not individual genius. Einstein was wrong about hidden variables, but the scientific process eventually demonstrated this through experiments, not authority or preference. Bohr was wrong about complementarity being the final word, but his insights advanced the field. Schrödinger disliked the probabilistic interpretation of his own equation, but the mathematics spoke more clearly than personal preferences. Nature, not human authority, decides which theories survive. Anyone can propose alternative theories. Crackpots regularly claim to have disproven quantum mechanics or discovered new physics. If their theories make different predictions from quantum mechanics, experiments will decide, not opinions or personal intuitions. This is both humbling and liberating. No amount of intellectual authority, academic credentials, or forceful personality can override experimental evidence. This empirical democracy, where nature serves as final arbiter, distinguishes science from other modes of knowledge and guarantees its cumulative progress. Religious authorities might declare truth by fiat. Philosophical schools might argue indefinitely about fundamental principles, but science must ultimately answer to experimental evidence. This is both science's greatest strength and its most humbling characteristic. Reality has the final word. Quantum physics isn't strange. It's simply different from what we expected, and our brains are flexible enough to eventually adapt. Students learning quantum mechanics initially often struggle, fighting against classical intuitions that served them well in everyday experience. But with practice, patience, and proper mathematical preparation, they develop functional intuition that enables productive application of quantum concepts. This quantum intuition doesn't replace classical intuition for everyday situations. Both coexist, applicable in different appropriate domains of experience. A mature physicist knows when to apply each type of thinking, fluently transitioning between classical and quantum descriptions as situations demand. Working with macroscopic objects. Think classically, designing semiconductor devices. Think quantumly. The skill is knowing when each framework applies. This conceptual flexibility is a learned skill, not an innate gift. Anyone with sufficient dedication can develop this flexibility through study and practice. The ability to think quantumly isn't restricted to genius-level intellects or special talents. It requires patience, mathematical preparation, willingness to abandon preconceptions, and tolerance for initially uncomfortable concepts. But these are achievable goals for dedicated students. Thousands of physicists and engineers apply quantum thinking routinely in their work. They design quantum devices, calculate molecular properties, predict material behaviors, and solve practical problems using quantum mechanical principles. For them, quantum mechanics isn't mysterious philosophy, but working knowledge. They've developed the mental tools necessary to navigate quantum reality professionally and productively. The final message isn't that quantum mechanics is incomprehensible, but that comprehension requires abandoning expectations and embracing the universe on its own terms. We must stop demanding that reality conform to human psychological preferences and instead adapt our thinking to reality's actual structure. This represents intellectual maturity at the highest level. The universe isn't wrong. Our provincial intuitions were mistaken from the beginning, shaped by evolutionary pressures irrelevant to fundamental understanding. We evolved to survive in environments of intermediate scale, moderate speeds, and familiar energies. Nothing in our evolutionary history prepared us for atoms, high-speed particles, or quantum superposition. The fault lies not in reality, but in our assumptions about reality. Quantum physics works perfectly, predicting with extraordinary precision phenomena from electron scales to collapsed neutron star properties. Every technology depending on quantum mechanics functions exactly as theory predicts, billions of times per second in devices worldwide. Your computer processor, your smartphone screen, your LED lights, your solar panels. All quantum mechanical devices working exactly as the equations predict. This practical success confirms that whatever the deep philosophical meaning, the theory's mathematical structure captures something profoundly real about nature. The mathematics isn't just human invention or convenient approximation. It describes actual features of reality's structure, verified through countless experiments and technological applications. The universe really does behave quantum mechanically. The strangeness isn't in the physics. It's in us, in expectations we brought based on experiences that didn't prepare us for what we'd find. The more we learn about the universe, the clearer it becomes that it wasn't designed to comfort human intuitions or satisfy desires for easy understanding. The universe has its own logic, its own principles, its own way of operating that we must learn to accept. But it's also clear that the universe is comprehensible. With mathematics and experiment, we can map conceptual territories that direct experience never could reach. We can understand the behavior of objects trillions of times smaller than anything we can see, predict the properties of materials not yet invented, and comprehend the quantum processes powering stars. Comprehensibility doesn't require intuitive comfort. Quantum physics simultaneously demonstrates natural intuition's limits and the power to transcend those limits through rigorous systematic method. We are limited creatures discovering unlimited truths, finite minds contemplating infinite structures, brief existences touching eternity through science. This represents something unprecedented in the known universe. Matter has achieved sufficient complexity to understand its own behavior. Quantum physics isn't the end of mystery, but revelation that the universe is more mysterious and wonderful than any previous imagination conceived. Each answer reveals new questions, each discovery opens unexpected horizons, each generation inherits mysteries and bequeaths others to successors. The process appears inexhaustible, as if mystery is built into reality's structure. The invitation remains open. Abandon the illusion that the universe must conform to human expectations and embrace the adventure of discovering what actually exists. This requires intellectual courage and humility, willingness to be surprised by reality rather than demanding that reality conform to prejudices. It's perhaps the most mature relationship possible between mind and cosmos. Quantum mechanics is just one chapter in this cosmic adventure of self-understanding. Probably neither the strangest nor the last we'll discover. The universe is 13.8 billion years old. Humans have existed for a few 100,000 years. Quantum physics has only a century of development. We're at the very beginning of understanding, not approaching its end. How much more remains to be discovered? How many conceptual revolutions still await? What unimaginable truths will future generations consider obvious and trivial? The journey continues, and quantum physics is a permanent invitation to participate in this collective exploration that defines what it means to be thinking human beings. This isn't just about understanding physics. It's about understanding our place in a universe far stranger and more wonderful than our ancestors could have imagined. Every time we probe deeper into quantum reality, we discover not just new facts about nature, but new possibilities for what minds can achieve when properly equipped with mathematical tools. Consider what this means for human civilization. We've gone from not knowing atoms existed to manipulating individual electrons in less than 2 centuries. We've progressed from thinking light was purely waves to building devices that exploit its particle nature. We've moved from deterministic clockwork models to embracing fundamental uncertainty while gaining unprecedented predictive power. This intellectual transformation represents one of the greatest achievements in human history. The universe isn't strange, quantum physics isn't strange. Only our original intuition was broken, and now we have tools to fix it. We spent millions of years developing mental models suited for hunting game, gathering plants, and navigating social relationships among small groups. These models served us well for survival, but proved inadequate for understanding fundamental reality. The mismatch isn't reality's fault. Think about the evolutionary pressures that shaped human cognition. Our ancestors needed to track animals moving at speeds of 10 to 30 miles per hour across landscapes measured in miles. They needed to throw spears at targets a few dozen yards away, predict weather patterns over days or weeks, and remember the locations of food sources across territories spanning perhaps 100 square miles. Nothing in this environment prepared minds for understanding particles moving at speeds approaching 186,000 miles per second through spaces measured in billionths of inches. Reality doesn't need to make intuitive sense to function perfectly, and it does function regardless of our understanding or psychological approval. The atoms in your body don't wait for your permission to exhibit quantum behavior. Electrons in your smartphone's processor don't pause their tunneling until you feel comfortable with the concept. The universe operates according to its own principles, not human preferences. This indifference to human psychology is both humbling and liberating. Transistors work because electrons tunnel through energy barriers in precisely the ways quantum mechanics predicts. Lasers work because atoms emit coherent photons through stimulated emission, exactly as quantum theory describes. MRI scanners work because nuclear spins precess in magnetic fields according to quantum mechanical principles. GPS satellites work because atomic clocks maintain quantum mechanical precision while accounting for relativistic effects. Every electronic device around you, every medical diagnostic tool, every precision instrument, every communication system depends on quantum mechanical principles working exactly as the theory predicts. The evidence surrounds us constantly, integrated into the fabric of modern technological civilization. We live in a quantum mechanical world, whether we acknowledge it philosophically or not. If the theory seems strange, the problem is in us, not in the theory or the universe it describes with repeatedly verified precision. We can choose between resisting this conclusion and remaining confused, or accepting it and developing new intuitions compatible with what we've discovered. The first option leads to perpetual bewilderment and missed opportunities. The second opens unlimited possibilities for understanding and technological advancement. The second option is more difficult but infinitely more rewarding, opening understanding of wonders that resistance would perpetually keep hidden. Students who struggle initially with quantum concepts but persist through the discomfort often report transformative experiences. Suddenly the mathematical formalism clicks, the experimental results make sense, and a new way of thinking about reality becomes available. It's like learning a new language that reveals previously invisible aspects of the world. This transformation isn't just intellectual but practical. Engineers who master quantum mechanics can design devices impossible to conceive classically. Chemists who understand quantum orbitals can predict molecular behavior and design new materials. Physicists who embrace quantum thinking can explore realms of reality completely inaccessible to classical analysis. The conceptual tools unlock practical capabilities. Quantum physics isn't the end of enchantment with the universe. It's the beginning of deeper enchantment based on verifiable reality. The classical world of clockwork determinism, though comforting, was ultimately a shallow picture of what exists. Quantum reality reveals layers of structure, possibility, and connection that classical thinking never suspected. The universe is far more interesting than we imagined. Consider the implications of quantum entanglement. Two particles separated by thousands of miles remain connected in ways that Einstein called spooky action at a distance. This isn't science fiction or mystical thinking. It's experimentally verified reality with practical applications in quantum computing and cryptography. The universe maintains correlations across vast distances without any apparent mechanism for communication. Mystery doesn't disappear with explanation. It deepens, revealing layers of structure and elegance that previous ignorance didn't even suspect existed. Each answer about quantum mechanics generates new questions about deeper levels of reality. Why does the universe permit quantum behavior? What determines the values of fundamental constants like Planck's constant or the electron charge? How does classical reality emerge from quantum foundations? The more we learn, the more sophisticated our questions become. Every physicist contemplating quantum equations working perfectly feels renewed admiration for the extraordinary mathematical structure governing material existence. This admiration isn't mystical or irrational. It's the appropriate response to discovering profound order where apparent chaos initially seemed to reign. The beauty of quantum mechanics lies not just in its predictive power, but in its mathematical elegance and internal consistency. The universe could be chaotic, incomprehensible, arbitrary. Instead, it obeys elegant mathematical laws that finite minds can discover and apply. Think about this remarkable fact. Collections of atoms organized into human brains can understand the laws governing individual atoms. Matter has become sufficiently complex to comprehend its own behavior. This is unprecedented in the known universe and represents something approaching the miraculous. This fact has no known explanation. It's a primordial mystery that all physics assumes, but doesn't fundamentally explain or clarify. Why does anything exist instead of nothing? Why laws instead of chaos? Why laws that minds can discover? Why mathematical relationships instead of arbitrary behavior? These questions remain open, representing the deepest puzzles about existence itself. Quantum mechanics adds to the mystery rather than resolving it. Quantum physics answers many questions but generates others, as all good science does, pushing knowledge boundaries ever further beyond current understanding. The Manhattan Project used quantum mechanics to build atomic weapons, revealing nuclear physics principles and raising questions about fundamental forces. The laser emerged from understanding stimulated emission, but opened investigations into nonlinear optics and quantum field theory. Transistors revolutionized technology through quantum mechanical semiconductor physics, but led to questions about many-body quantum systems. Each application revealed new phenomena requiring explanation. Superconductivity was discovered through quantum mechanical analysis, but required new theories of electron pairing. Quantum tunneling explained radioactive decay, but opened questions about barrier penetration and quantum field fluctuations. The quantum Hall effect revealed new states of matter with topological properties. Every answer spawned multiple new questions. The universe owes no explanations to human intuition, and that's the central lesson that 100 years of quantum mechanics repeat incessantly in every experiment. Our intuition was forged under conditions completely irrelevant to fundamental reality, and its inadequacy doesn't reflect universe failure, but our contingent origins. We evolved for survival, not for understanding atoms, photons, or quantum fields. The capacity to recognize and transcend this inadequacy through reason and experiment represents mind's triumph over inherited biological limitations. We need not remain prisoners of intuitions shaped by survival on African savannas. We can construct new conceptual instruments adequate to discovered realities. This represents intellectual evolution beyond biological constraints, the emergence of purely cultural and scientific ways of understanding. Quantum physics is one such instrument, painstakingly constructed over a century by hundreds of minds collaborating across generations. Planck's initial insights about energy quantization, Einstein's photon hypothesis, Bohr's atomic model, Heisenberg's uncertainty principle, Schrödinger's wave equation, Born's probabilistic interpretation. Each contribution built on previous work while adding essential new elements. We inherit this instrument ready for use. We can employ it to understand and transform reality in ways its original builders barely imagined. Smartphones contain billions of quantum mechanical devices operating billions of times per second. Quantum computers promise revolutionary computational capabilities that could solve problems intractable for classical machines. Advanced materials with precisely engineered quantum properties enable technologies from superconductors to photovoltaic cells to quantum sensors. Medical therapies increasingly depend on quantum mechanical understanding of molecular interactions. Drug design uses quantum chemistry to predict how molecules will bind to biological targets. MRI imaging exploits nuclear quantum spin to visualize soft tissues. Radiation therapy uses quantum mechanical calculations to optimize dose distributions. Quantum biology reveals quantum effects in photosynthesis, enzyme catalysis, and possibly even consciousness. But beyond practical applications, there's intrinsic value in understanding existence's fundamental structure, satisfying curiosity that defines thinking humanity. We want to know how the universe works, not just to manipulate it, but because knowing is valuable in itself for creatures that value truth. This pure curiosity drives much of fundamental physics research and represents something uniquely human. Quantum physics satisfies this deep curiosity by revealing that reality is richer, more subtle, and more elegant than simple intuition would ever suggest. The quantum universe is a place of possibilities, probabilities, and interconnections that transcend classical locality while remaining perfectly mathematically comprehensible. It's a reality where information can be fundamentally uncertain, where distant particles remain connected, where measurement creates rather than merely reveals properties. Understanding this universe is a privilege no previous generation possessed, and that future generations will expand in ways we cannot yet imagine. We're the first humans to glimpse quantum reality's true nature, the first to manipulate individual atoms, the first to harness quantum effects for technology. Future generations will build on our foundations, developing deeper insights and more powerful applications we can barely conceive. The quantum revolution is just beginning. Quantum physics isn't strange. It's simply true, and truth has no obligation to conform to expectations derived from partial and limited experience. If there's strangeness, it's in us, in brains shaped by circumstances irrelevant to fundamental understanding, now transcended by adequate conceptual instruments. The universe operates according to quantum principles whether we find them comfortable or not. The universe functions perfectly according to quantum mechanics. That's the final lesson. Simple yet profound, uncomfortable yet liberating from illusions. Every measurement confirms quantum predictions. Every technology validates quantum engineering. Every experiment supports quantum theory. The evidence is overwhelming and continues accumulating daily through countless applications and investigations. Accepting this lesson isn't defeatism or conformism. It's intellectual maturity that permits genuine progress beyond self-imposed barriers of inadequate expectation. We can continue demanding that reality conform to human preferences and remain perpetually confused, or we can adapt our thinking to reality's actual structure and unlock unlimited understanding possibilities. The adventure of comprehension continues, and quantum mechanics is a permanent invitation to participate in this exploration that defines the best of human condition. Every student learning quantum physics, every researcher probing quantum phenomena, every engineer applying quantum principles participates in humanity's greatest intellectual enterprise, understanding the universe that created us. The universe isn't strange. Its physics is elegant and consistent. Only our original intuitions were mistaken, and now we know better through science. Quantum physics works, reality works. Both will continue working regardless of our understanding or approval, indifferent to human psychological discomforts. The problem was never the universe. The problem was always us, and recognizing this is the first step toward genuine and lasting comprehension of reality. If you're still awake, it's because the content was really good. So take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.